Last time, we introduced the Landau's free energy in the case of inhomogeneous distribution of your magnetization over the real space, and we could define so-called the block spins by partially integrated over the microscopic details, degrees of freedoms over a small size. But that small size is actually larger than the unit cell with length scale A over the lattice. In other words, we actually partially sum over the partition function or a trace over the block spins. Okay, a group of local spins. Rewrite this partition function in terms of this Landau's free energy functional by including the spatial inhomogeneous of this magnetization distributions, and we would like to minimize such inhomogeneous distributions of this magnetization. We need to add this gradient m squared in this Landau's free energy functional as a so-called coarse grain free energy. Today, we will start from here, Landau's free energy over this coarse grained lattice, and we show that this Landau's free energy is not what we are familiar with the so-called Gibbs free energy in the statistical mechanics sense. In other words, Landau's free energy functional is a special kind of free energy, which is related to the Gibbs free energy, but only in the sense of a coarse grain type of a Gibbs free energy, which we will discuss later today. But let us just interpret properly Landau's free energy in terms of statistical mechanic well-defined free energy, so-called Gibbs free energy. The Gibbs free energy, StatMech, is defined by this free energy, so-called Helmholtz free energy, plus the term where you have this external magnetic field coupled to magnetization, M. And you have n such spins. Altogether, you get the Gibbs free energy. So we could define this Helmholtz free energy by simply just trace over this Hamiltonian H omega of your statistical system. Remember that the external field, which is a function of magnetization, defined by this equation that minus partial F partial H, where H is the external field, is given by the number of your spins multiplied by the magnetization. In other words, external field is actually the field that is required to have such a magnetization M. So now we're going to argue that this gamma as function of external field that we defined over here through this Gibbs free energy is not the Landau's free energy L that we defined over there. So the reasons are twofold. The first reason is that this Gibbs free energy is actually the convex down function. Okay, remember, very beginning of this course, we plot this free energy as a function of magnetization, and we argue and we prove mathematically that this free energy density as a function of magnetization is actually convex down as a function of this M. Remember that. All right, but this Landau's free energy, L, is not a convex function. So we will see in just a moment. So that's the first reason that they are not the same, but they are closely related, as we will explain in just a moment. And the second reason why these two quantities are not the same is that the Gibbs free energy is actually a thermodynamic function. In other words, we already trace all the states when we calculate this Gibbs free energy. All the microscopic states are integrated over when we get this Gibbs free energy. So in particular, in Landau's free energy, we talk about this coarse grain, kind of a group of spins that's actually the basic unit in this Landau's free energy, where we integrate out the degrees of freedom only within each coarse grain unit. But here, the Gibbs free energy is actually already integrated over all the microscopic degrees of freedom. In other words, all the spatially variant function magnetization as function of this coarse grained coordinate has no meaning here, because when we get this Gibbs free energy, we already integrated out all the microscopic degrees of freedom, so all the spatial information has been integrated all over already. Therefore, for these two reasons, they are not the same. But let's just look at some details. For example, this convex function of this Gibbs free energy. but this Landau's free energy is not a convex function. So let's just prove this. The first property of a convex nature of this free energy. So suppose we take the partial derivative of Gibbs free energy with respect to this magnetization, following this definition over there. Also, we notice this partial F, partial H from that definition is nothing but minus n times m. If we simply just take this derivative of Gibbs free energy with respect to this magnetization, and by plugging this relation between the external field and the partial F, partial H, then we get this simple result that this partial derivative of Gibbs free energy with respect to magnetization is given by n times h, because the first term is cancelled with the last term. So you notice that if there's no external field, there's no magnetization. So in other words, this partial Gibbs free energy, partial magnetization is actually 0 here. But it looks similar to the minimization of the Landau's free energy with respect to its mean field phi, but in fact, this is not the same. So let's just look at how different they are in just a moment. In the absence of the field, it looks like we can define the Landau's free energy in terms of the Gibbs free energy. But let's just generalize this zero field impression at the finite field and see if that kind of identification makes sense or not. In fact, this identification is not correct. But let's just go through the argument. In the presence of the external field, H is not equal to 0, we can identify a candidate or propose a candidate for Landau's free energy, which we call the L prime, in terms of the Gibbs free energy, and subtract by a term which coupled to the external parameter, such as the external magnetic field. And so we plug in this Gibbs energy in terms of this F plus m times h as function of the m, but we simply just subtract this by external field. Okay? So this h hat in general is an independent parameter from the field in the definition of a Gibbs free energy. Okay, suppose that this h hat is kind of an independent external field, and we will show later that in some simple cases this h hat is actually the same as the external magnetic field. So we can always satisfy this kind of a vanishing of this partial derivatives L prime with respect to this mean field magnetization. Okay, and we can actually demand that this equation to be satisfied, and we can always find such a way to actually satisfy this kind of mean field equation that we found by minimizing the Landau's free energy with respect to the order parameter phi. Okay, the way that we could do such an identification is that if we actually expand this partial derivative L prime with respect to m, we could easily find that we get this kind of identity which allows us to actually identify this h hat as simply just external field, because we could easily see that the last term of this partial derivative vanishes, so you end up with this simple relation that this partial Gibbs free energy partial m is actually the same as h hat times n, but then you can rearrange this equation to get this kind of identity, but you know that partial Gibbs free energy partial mm is actually the same as this external magnetic field, but that external field is actually the same as h hat. So suppose I could choose h hat as external magnetic field, and I can always satisfy this kind of Landau's equation for order parameter phi. However, such an identification is not correct. Okay, so let's see why this is not correct. So in the absence of the external parameter h hat being 0, in such a case, this L prime is nothing but the Gibbs free energy. Right? So if h hat is actually 0, then they are the same. Okay? But we know that they are not the same. So how come? Well, you can simply just use this kind of plot that we had before, which is the free energy as function of the external magnetic field for Ising system, where you can find a cusp, right, in the thermodynamic limit, which we already show. And also the magnetization function of the external field, which shows spontaneous magnetization for a slightly positive negative field, you get plus m or minus m magnetization value. and there's a jump between plus and minus m magnetization right at h equals 0. So in other words, you get non-zero magnetization at zero field, in between this plus and the minus ms. Therefore, you could actually plug in this. So this little f is actually free energy density in this case. So you simply just plug in these two figures back to the Gibbs free energy formula, right? And then you could make a plot of this L prime in this zero field limit, which is the same as the Gibbs free energy as functions of n. And you can check by yourself that the whole plot is actually a U-shaped figure, where between this plus and minus ms, this Gibbs free energy, or this your new Landau's free energy, is actually a flat constant, okay, where you get zero first derivative of this Gibbs free energy with respect to the magnetization. Okay, so indeed this is actually the convex function in M. Okay, however, this function is not entirely the same function as the Landau's free energy. Remember, Landau's free energy as function of Euler parameter shows double well. Okay, so in the region outside of this spontaneous magnetization, you get a convex function in both true Landau's free energy, functional, as well as your candidate or proposal for Landau's free energy in terms of the Gibbs free energy. So the Gibbs free energy does give rise to the convex, or it's kind of a parabola that we see from the Landau's free energy. But within this range between plus and minus ms, they are not the same. Because on the left-hand side, the Gibbs free energy is actually flat. However, we know that the Landau's free energy, in terms of the magnetization, leads to the double well. And it is the Landau's free energy, which is what we want. And therefore, in general, this Landau's free energy cannot be just constructed in terms of the Gibbs free energy, because the Gibbs free energy always gives you kind of a flat constant in between this plus or minus ms, okay? Where the real Landau's free energy shows such a double well structure, which is what we really need, okay? And therefore, we mathematically show that the Landau's free energy is not the same as Gibbs free energy, okay? But they are closely related to each other, so we will see how they are related to each other in just a second, okay? But in one sentence, if we don't integrate out all microscopic degrees of freedom for Gibbs free energy, then the Gibbs free energy, the coarse-grained Gibbs free energy, so to speak, is actually Landau's free energy that we want. In other words, Landau's free energy is nothing but partially integrated Gibbs free energy. Okay? So we will see that kind of a partially traced partition function, and to identify the Landau's free energy in terms of the Gibbs free energy in just a second. Okay? So you could easily plug in this kind of figures that were already learned in the past and plug into this Gibbs free energy, and you see indeed that this is a U shape with a flat in between. Okay, so now let's take a break, and when we come back, we will again link the coarse-grained Gibbs free energy to the Landau's free energy. So we just proved that the simple statistical ensemble average Gibbs free energy cannot be the same as the Landau's free energy. Okay, but they are in fact closely related. So what's the connection between these two? Well, in short, the Landau's free energy is nothing but the coarse-graining Gibbs free energy. So by coarse-graining, I mean we simply sum over the microscopic degrees of freedom just partially, right? Not fully sum over all the microscopic degrees of freedom. In other words, we can define this Landau's free energy, L, as Gibbs free energy constrained to be in the configuration specified by this block spin magnetization. Remember the block spin. Okay, the block spin is a bunch of the spins inside the region which is larger than the lattice spacing A, but smaller than the coherence length, the correlation length. But there are many such M, and inside each of this block spin, and there are also many different ways to actually get such a magnetization M within each block. For example, suppose we consider the magnetization that's just Landau's order parameter phi for the Ising spin. Then suppose there are a couple of spins within such a bigger unit cell, which we call this cluster or block spin. Then all the spins are pointing up except one spin. The last spin is pointing down, but this state is actually the same as all the spins are flipped. Suppose we flipped up spin to down spin and down spin to up spin, then the second configuration is actually identical to the first configuration. So there's sort of a degeneracy when we specify this the block spin M. Okay, so just remember that there's some degeneracy there. But how do we get the Landau's free energy? By partially summing over the microscopic degrees of freedom within the block spin. So this is what we do. The formal definition of the Landau's free energy as function of the block spin, e to the minus L divided by kBt, is defined by this trace over the microscopic degrees of freedom within each of a specific unit cell of a block spin. And we have this kind of a Kronecker delta function which specify this block spin configurations. Namely, suppose there are many such the spin within each block, then we simply just sum over all this microscopic degrees of freedom within such block, and we should get this equation to be satisfied. Namely, when we sum over all this microscopic spin within each block, this is the same as the number of spins multiplied by the magnetization within such a block. In other words, this block spin is actually kind of a fluctuating magnetization over this real space coordinate, but more or less it is just a uniform kind of a background within such a block. So you could actually consider this kind of a red curve as a realistic profile of magnetization over entire one block, and there's little up and downs here, but on average you can actually see that there's some sort of a background average of this magnetization over entire block, but within such a block it is actually larger than this lattice constant A, much larger than this lattice constant A. So within such a kind of a median-sized block, there are many spins. But suppose we sum over all the spin moment within such a block, you should be able to get to this average value of this magnetization in the entire block multiplied by the number of spins within such a block. But we only trace over that particular block, and we don't care about the other block when we say so. But you could actually consider this kind of a Landau's free energy or cross-grain Landau's free energy as function of all this real space vector R or real space location. You could actually do the same thing for all the other blocks. Here, I simply just define my cross-grain Landau's free energy density for such a specific block spin. But you can do the same thing for the others. So this delta K is actually Kronecker delta function. Within this argument A minus B, this is actually 0 if A is not the same as B, and it is 1 if A is equal to B. So you can see that this kind of partial trace of microscopic degree of freedom within each block is actually not the same as tracing over the entire microscopic degrees of freedom when we compute the partition function. So it is simply just a subset of all the terms that we should trace over when we calculate the partition function. It is just a partial terms within this whole partition function Z. So in other words, this is not the same as the partition function, and therefore if we take this minus kBt log Z, then of course this Landau's free energy is not the same as the Gibbs free energy, where the Gibbs free energy is the free energy that is obtained by this partition function. But this Landau's free energy is a partial trace of this partition function. And that explains why the Landau's free energy is not the same as Gibbs free energy, because Landau's free energy is only the partial trace of this partition function. All right? But let's just look into the definition of the partial trace once more. So as I mentioned, this trace prime denotes the summation over microscopic degrees of freedom that is consistent with the magnetization within the Bloch spin n. But we know that there are many other blocks and many other microscopic degrees of freedom for the whole thing. So for those of spins which are not belonging to the specific Bloch spin, we denoted this by Si star, which simply just tells us all the other slowly varying order parameter of other blocks. Therefore, you could simply just decompose this trace over or summing over all the microscopic spin degrees of freedom in terms of the product of these two summation. And the first one is summing over a particular Bloch spin degrees of freedom, and the second thing is actually summing over all the other remaining microscopic spin degrees of freedom, which I call this S star. And therefore, the whole partition function, which is trace over or sum over entire microscopic spin degrees of freedom of all system e to the minus beta h, could be decomposed in terms of the product of these two kind of summations, partial summation. One is trace prime, okay, which is exactly what we defined there for the Landau's free energy functional. But there is another remaining summation over S star, which is all the other degrees of freedom. But we could certainly just insert our definition of Landau's free energy over there by partially summing over the microscopic degrees of freedom within each block. As a result, the whole partition function is nothing but the summing over all the blocks of degree of freedom S star. But within such a summation, we already have the partially traced Landau's free energy, a coarse-grained Landau's free energy within each block. So let me just interpret this term one more time. When I write this e to the minus beta L, I mean that I already defined all this, say, partially traced Bloch spin for each of these blocks. But I have not summed over the entire blocks. I only defined my Landau's free energy within each of these Bloch spins. But I have not summed over all the other blocks. And when I sum over all the blocks, I mean I should sum over S star. The S star refers to all the independent blocks that remain to be summed. And therefore, if I could actually decompose my entire trace, to get to the partition function in terms of different ways, I could actually simply just sum over entire microscopic degrees of freedom one by one. So that's the first approach. But I can also perform the trace from a different route, which is following that route. I can actually, first I sum over the microscopic degrees of freedom within each block, and then I sum over all the blocks. So it's kind of a two-step summation. I first focus on this microscopic degrees of freedom within each block, but I know that I need to sum over all the blocks. Then I can actually decompose that kind of summation into the first summation over the microscopic degree of freedom within each block, and then I multiply the summation over the entire different blocks. Okay, so when I perform two-step summation, I get back to the full trace of the partition function. Everybody get that point? Okay, because the trace is actually summation over all microscopic degrees of freedom. I can decompose such a kind of summation into two different summations, and then actually multiply this kind of two summation together. Because when you expand this kind of a product of these two separate summations, you get back to all the terms inside the trace. When you compute the partition function, you can check that. right? So, and we should actually make a product of these two summations to get back to this, the full summation of all microscopic degree of freedom. Okay, so that's a mathematical derivation that you could check, but I'm telling you that this is another way to perform the trace. But this is a better way because now we could actually define a cross-grained Landau's free energy, L as function of this block spin magnetization. And from that behavior, we know how the order parameter actually influences this Landau's free energy and whether there's a single minima or double minima or global or local minima, and whether you can find the magnitude of this first derivative of Landau's cross-grained free energy with respect to the order parameter, and you get the phase transition. So there are a whole bunch of advantages by using the cross-grained Landau's free energy rather than this kind of the full trace of your microscopic degree of freedom, because when you full trace everything, you simply get just a macroscopic, not a microscopic degree of freedom. Here, we partially trace over a microscopic degree of freedom up to a certain region, then we get kind of an intermediate scale free energy, and that intermediate scale free energy helps us to understand the phase transition. So we don't need, and it's not useful to actually directly compute the whole thing by tracing over all microscopic degree of freedom to get the phase transition, because, as I mentioned, there's no information about this local fluctuation and so on. Okay, if we simply trace over all microscopic degree of freedom, and this kind of information, local information, is lost. So the gain that we make by defining such a partial trace in the partition function is to actually gain the information about this kind of a local profile or real space configurations of this local spins, not just the ensemble average quantity. So when we sum over entire microscopic degree of freedom and we don't have any information at the local scale, okay? But the local fluctuations play a very important role near the transition. So that's the reason why we need to keep this kind of a partial trace and define this coarse-graining Landau's free energy. But we will explain a little bit more when we get to this point, fluctuations beyond this Landau's mean field theory. Many of the fluctuations involve spatial fluctuations and kind of deviations from the mean field variables. Okay? Therefore, the best way to study the phase transition is precisely following Landau's prescription that we define the coarse-grained Landau's free energy, and we study how this L behaves as a function of this local magnetization M within such a block. Okay, so this is a very important step in order to understand better the Landau's approach. So we know that the Landau's free energy is nothing but this partially traced partition function, and also it's a cross-grained Gibbs free energy. And therefore, we could think of this partition function as just integration over the, say, block spin variables or block spin magnetization M, and inside the integrand, this is e to the minus beta Landau's free energy, L. And within this each block, we have such a constraint that you sum over all this microscopic degree of freedom, and you get the number of spins multiplied by the average magnetization for the entire block. And so we can use this order parameter in the Landau's language by rewriting the partition function in terms of the trace over this order parameter phi as function of R, where R is kind of a real space labeling of this block spin variables. And we remember the Landau's free energy is actually an integration over the space of a d-dimensional space, and inside the integrand, it is the Landau's free energy density, which is gradient phi squared plus phi quartic, and subject by this Zeeman term, h times phi. So the original spin degree of freedom Si, where I runs from 1 to to actually all this number of spins. But here we use this kind of a continuous variable r for this block spin, okay, or the order parameter in real space. And in particular, we consider a situation that the system is actually in a continuous limit, namely if this lattice constant is actually 0, shrinks to 0, and the number of spins goes to infinity. Okay, but the volume is still a constant. Okay, in that continuous limit, we are able to calculate the partition function in such a coarse-grained Landau's formalism here. And in that case, all this phi could actually goes either discrete sense or in a continuous limit. All right. So in the discrete version, it is simply the product of all this little volume with d phi in real space, but in the continuous limit, we can actually use this r to label all these block spins, and then we can integrate over the entire block spins degrees of freedom, dm or d phi. So to do so, we need the Fourier transform from this real space to the momentum space or the Fourier space. Okay, so imagine that the order parameter phi is actually a real space function, but it's actually not just a uniform constant value function, but it fluctuates from one side to another, and you can Fourier transform this real space representation of this order parameter and look at this trace in K space. Okay, so we'll see in just a moment that this is a convenient way of calculating the partition function by going to the Fourier space. Okay, so to do so, we could just simply perform the Fourier transformation of this order parameter, phi of r to phi of k in K space or Fourier space, and we could integrate over the entire, say, momentum of K degrees of freedom, say from 0 to infinity, where upper bound is actually 1 over the lattice constant, which goes to infinity. Okay, but we could simplify this calculation by taking advantage of the relation between this phi k and phi minus k in real and imaginary part, and in particular in the real parts they are equal. So this phi of k is actually the real part is actually the same as a real part of phi minus k, but in the imaginary part we get the minus sign here. So we can actually restrict the region of integration to half of the k space value or the k values, such that the trace actually go to just a half of the degrees of freedom. Okay, we'll restrict ourselves to the positive value of k, because the negative value of k, we can actually use that relation to link the results in the other side. All right, okay, so we could actually Fourier transform this phi of r to k space order parameter, which we call this phi of k, and you could inverse Fourier transform this phi of k back from this phi of r, and the delta function is given by sum over k, this e to the I k dot r minus r prime. So this is just a simple Fourier transformation, and we could again use a continuous integration to actually evaluate this discrete summation over this Fourier variable k. And these are just some simple relations when we Fourier transform this order parameter. So we achieve two goals. Number one, we show mathematically and rigorously that the Gibbs free energy is not the same as Landau's free energy. Okay, and second, we show that what is a Landau's free energy? Well, it is simply the coarse-grained Gibbs free energy, which we partially trace out the microscopic degrees of freedom within each block spins. Then we can represent the partition function in terms of the block spin integration, and the integrand is nothing but e to the minus beta times Landau's free energy density. In other words, Landau's free energy is nothing but kind of intermediate free energy profile as a function of local parameters, okay, or order parameters in terms of real space variables. Whereas the Gibbs free energy is a fully traced quantity that comes from the partition function itself. So next time we will start to evaluate this partition function and also the Green's function, the correlation function, in particular the real space correlation function that we calculated for the Ising model. And we will actually perform such a calculation, but in a more systematic way, that we are able to get the spin-spin correlation function for arbitrary two spins in any dimension. We are getting the more interesting part of this course, namely to analyze and calculate this Landau's free energy density and then study the critical properties and correlation functions near the transition in a more systematic and rigorous way. See you on Thursday then.